Hello and welcome back to another video in the physics lecture series. In this video we're going to discuss the comparison between the series and the parallel circuits. In the last two videos, series circuit analysis and parallel circuit analysis, we looked at two different arrangements of the same elements. We had a battery in each, and I made it 12 volts. We had a 2, 4, and 8 ohm resistor in the first arrangement in series. Each element came after the other, but in parallel, each one split off from a main branch. So let's take a look at how easy the solution to problems like this really is. Both series and parallel circuits both have the same 4 steps. Here they are in summary and comparison. The first step is to find the equivalent resistance of each or either kind of circuit. So if you're dealing with a series circuit, you're going to use a straight sum. You're just going to add up the 3 resistors. But if you're dealing with a parallel circuit, you have to use the inverse resistance rule, and that is right here on the reference table. Right here. So if you add them up, you're dealing with series. If you add the inverses, you're dealing with parallel. The second step is to use Ohm's law to find the total current. And then the third step, which is really the only difference, a series has all the currents being the same, so you just use Ohm's law and you solve for the voltage drops or the energy spent at each light bulb, the energy required to push through that resistance. And of course, if you're dealing with a parallel circuit, the branches have their own individual currents because each branch is connected to the same junction. So they all have the same voltage across them, all 12 volts. Okay? And then power dissipation. Power is current times voltage. If the V's and the R's are given, we then forward solve. We go from steps 1, then 2, then 3, then 4. But if the V's or the R's are not given, we have to back solve using the other givens. You just follow the flow of this pattern to solve for what you need. It's very rare that on a real Regents exam you'll ever be asked to find every single value of every single resistor. You will find that they will leave out 1 or 2 things and you have to back solve to find them. Length of the problems that I gave you in the previous videos, which look like these, you will never be asked to solve for all of these things. This is a lot of work. Now they will ask you for 1 or 2, maybe 3. So let's take a look at the 2 problems compared side by side. So they both had 24 volts. 2, 4, and 6 ohm resistances were placed in series on one side and in parallel on the other side. So the equivalent resistance, when you added them up, you got 12, but when you inverse added them, you got 1.09. So if I just did a quick division, you see that there's a series to parallel ratio. It turns out to be 11 in this case. For the same elements in the circuit, one is arranged in series, one arranged in parallel. The series circuit always has more resistance. The parallel circuit always has less resistance. And so there's a direct consequence of that. More resistance means less current. Less resistance means more current. So we have an 11-to-1 ratio in resistance, and it's no surprise that we have an 11-to-1 ratio in the amount of current flow. So the parallel current, which had 11 times less resistance, has 11 times more current. All right, in the third step, we calculated voltage drops. When we added up the energy or the work done per unit charge to push through each of those resistors, it adds up back to the voltage of the battery. But if you're in a parallel circuit, you can see that the current splits in to the 3 branches, and the branch with the least resistance had the most current flowing through it, and the branch with the most resistance had the least current flowing through it. But still, when you added these back together, it added back up to the current that was determined in step 2. And then finally, we look at the power dissipation, the wattage. So the total power in the series circuit was 48 watts, but the arrangement makes all the difference in the amount of power that's used. Since you have so much more current, you're going to have so much more power distribution into each of the circuits. Again, a self-checking problem. Each one of the elements adds back up to the total for its kind. So 48 total watts added up to the total power used in a series circuit. And in this example, 528 watts was distributed among the 3 branches. A little something to look at. So you had the most current flowing through the first branch because it had the least resistance, and of course it had the largest value for wattage. And the reverse is also true. This branch 3 had the least amount of current because it had the most amount of resistance, and therefore had the least amount of wattage. And you add them back up, and you still come to the 528 for this problem. In conclusion, we're going to now look at the series and parallel circuits, all their formulas, and all their relationships. So you will notice up top here we have the 3 equation triangles. The first for current flow, the second for potential difference, also known as voltage, and the third for Ohm's law. So current flow is the charge flow rate. That's how much charge passes by in an amount of time. That's what defines what an amp actually is. 1 coulomb per second would be 1 amp. The potential difference is the work done per unit charge. That's the push. That's how the battery can push through the resistance. And then finally we have a relationship, the Ohm's law relationship, where the current is the V to R ratio. Let's scroll down a little more, and here we have the comparison of the 2 kinds of circuits. On the left I have the series circuit. On the right I have the parallel circuit. In between I have the circuit symbols extracted directly from the physics reference tables. The series rules I have extracted here on the left, showing that in a series circuit all the current goes through the only loop that there is, and therefore all of the energy is added back together to get you to the original battery voltage. And of course, the equivalent resistance of a series circuit is the sum of all of the resistances. Parallel circuits are a little different. Since there are 3 branches or 4 branches or whatever number that there might be, usually in a physics problem on the regions, there won't be more than 3 branches. You add up all the branch currents and you get the total current flowing through. But the voltage difference between the first node of the junction and the returning node of the junction always is the same, and we use the inverse resistance law. Now I put a little box in the middle about the laws of resistance. This has to do with the material that a wire is made from. So resistance is equal to rho L over A, where rho is the resistivity, which is a piece of information found on the reference table in this spot right here in the lower right hand corner of the electricity page. L is the length of the wire and A is its cross-sectional area. As L increases, R increases. As the area increases, the R decreases because they are inverse to each other. And this is the most important fact that you're going to be tested on. As the temperature increases, the resistance increases for a metal wire. Okay, there are 2 sets of rules that apply to the series versus parallel circuits. In a series circuit, there is always more resistance compared to a parallel circuit when they use the same components. 2, there's only one available path in the series circuit, so all components, whatever their resistance, have the same current flowing through them. 1 road, several tolls. All components use energy supplied from the battery. The more resistance, the more energy used by that component. So the higher the resistance, the higher the toll or the voltage drop. All the energy used at each component adds up to the total battery's voltage or potential difference. Now in parallel circuits, you'll see a little bit different behavior. So a parallel circuit always has less resistance compared to the series circuits which use the same resistors. The more branches in a parallel circuit, the less equivalent resistance. Therefore, it can allow more current to flow through. Many lanes, but the same voltage toll. The branch with the most resistance has the least current flowing through it. For a parallel circuit, the equivalent resistance is usually half of the smallest resistor value. When all the resistors are multiple of the largest, it is nearly half, proved by the 1 over Req formula. And finally, the equivalent resistance for identical components is the resistor value divided by the number of resistors. So the equivalent resistor, Req, equals R over the number of resistors. And we're going to look at a problem in a moment. Electrical power is the rate of doing work, but can be expressed in terms of current, voltage, and resistance alternatively. So power is work divided by time, and it's also IV, current times voltage. And there are two other expressions that can be derived from this, I squared R and V squared over R. Each of these expressions is a valid form of power based on available information. And here's a power triangle. Power is work divided by time. Work is in joules, time is in seconds, joules per second is watts. When you hook up an electrical meter in a circuit like we've done, you see that the voltmeter goes over the resistor and the ammeter goes through the resistor. So let's take a look. So here is the voltmeter. It goes over. It goes from this point over to that point. So I use a little mnemonic. It's pole vaulting, like pole vaulting when you jump over the bar. This is pole vaulting. And here is an ammeter. And so this goes through. The electrons have to go through it to be measured. The ammeter goes through the resistor. And here's a little mnemonic for that. Think of Amtrak. The train stays on the track. So Am for ammeter, Amtrak. All right, let's take a look at a brief example of a question that asks which circuit has the smallest equivalent resistance. And they show you a parallel circuit, a series circuit, a larger parallel circuit, and a larger series circuit. Notice they have all the same resistance values of 2 ohms each. We said before that there's this trick that the equivalent resistance is equal to the resistor value divided by the number of resistors. And here's the proof for that. So if you took the equivalent, 1 over R1 plus 1 over R2 plus 1 over R3, 1 over 4, and you put the 2 ohms there, you have 4 over 2, you got 2. And invert that, you get 1 over 2, which is 0.5. The formula is very simple to understand, that the equivalent resistance is equal to the resistor value over the number of resistance. I have a few rules here that I went over before. Parallel circuits always have less resistance compared to series circuits, which use the same resistors. And the more branches you have, the less equivalent resistance, and the less equivalent resistance you have, the more current you can draw into your circuit. So this concludes our video on the comparison between series and parallel circuits. Thank you for watching, and I'll see you in the next video.